7.1, systems and environments. So basically, I like to think of a system as comprised of two or more objects interacting with each other. So that's how I summarized the whole bit of 7.1. But then let's talk about some of the things that are in section 7.1. So I like to keep things as simple as possible. Let's see, systems consist or consists we're going to be dealing with closed systems. We're going to take these two objects and we're going to close it from the rest of the environment. We're going to close it off to friction and close it off to air resistance, close it off to anything that's not going to be part of our conservation of the physics that is within the system. We're going to be closing systems off to the environment when we're talking about conservation of energy, conservation of momentum, which are our two main conservation principles in physics. So let's get the basic definitions down first. So system consists of two or more objects interacting with each other. Keeping things simple, let's say that I have the ground here, and then I have a ball in space just hanging up there. Okay, well, this is a system between, so here's our Earth, and here's the ball. And so this system will be called the ball Earth system. We're going to close this system off to the environment that has, you know, nasty things about it. It's got friction out here, you know, air resistance, which is a form of friction. So just, you know, things that are going to take away from this system. We want to close it off in order to talk about how things like energy and momentum is saved or conserved. So our first conservation principle down the line will be the conservation of energy that exists within this system. All right, so that's what we have, at least visually, conceptually, that's going on with the concept of a system. So this would be a ball Earth system. The ball and the Earth will be interacting with each other in a particular physical way where we can discuss how energy, momentum can be saved. Ball Earth system. So as section 7.1 lays out, we're going to be focusing on the idea of systems in chapter 7 going forward, as opposed to just random particles as we've done in the previous chapters. All right, as I mentioned, we're going to isolate our system from the rest of the environment. The environment is just everything on the outside. The system is the object or objects in question. That's what we want to focus on. That's all that's important. The rest of the environment is going to complicate things. As we do in any good scientific experiment, we want to focus on one thing at a time, whether it's one particle or one system. Any one variable at a time, we want to focus on just that thing. So we're going to isolate the system from the rest of the environment. We can say, we can extend our environment to the universe if we want to do that, but it's all the stuff that's outside. We can say the environment is, say, the universe. And analyze the physics of and within that system. Okay, so we're only going to be concerned with things on the inside of the system. So a valid system, as I said, I like to just say two or more objects interacting. We're going to discuss what's going on between the two or more objects. So let's be complete. A valid system may be a single particle, kind of like the least case system. You can do that if you want. It's a collection of particles, a region of space, and it may vary in size and shape. Such that if a ball is thrown up against a wall, it temporarily deforms, and then as it rebounds off the wall, it regains its natural shape after that. And that's something that's going to be important when we're talking about momentum and impulse, which comes down in chapter 9. Yep.
Why would a single particle be a system?
It's generally not considered to be a system. I mean, it's all semantics at that point, but generally systems are just two or more objects, because when we talk about a system, we generally think of more than one thing. So I just think it's a matter of choice, but it's not really a big deal. Let me get that out of the way. Okay. Don't like when that happens. All right. So like I said, we will see in this chapter, we will see this chapter that, yeah, generally speaking, systems are more than one object. It's really non-essential to even get caught up in the fact that some people will choose it just for whatever esoteric reasons they want, but it's not a big deal. Will be comprised of an object or objects. Generally, we're going to be considering more than one. Interacting with each other. So as I mentioned before, we have our ball earth system. That's going to come important when we talk about how the energy that is stored between the ball and the earth is going to be converted into another type of energy called kinetic energy, or the energy of motion. So right now in this ball earth system, the energy, we're talking about energy, is going to be that of potential. You have the potential to convert to kinetic energy based on how high above the ground or the earth this ball is. So the higher the ball is above the earth, the more potential energy it has, and thus will have more kinetic energy the higher and higher the ball will be. So it's all directly related, and that comes later on. Nothing much about 7.1 outside of definitions and getting some idea of what a system is all about. So let's go on to 7.2. talk about the concept of work. Work done by a constant force, constant net force. So let's get right to the point. I'll just write that out. So let's get right down to it, right? Let's get to the point of things. The concept of work, not going to work or doing work around the house, physics work. So the concept of work in physics is defined as a net force multiplied by a displacement. We've seen objects displacing from one position to another. We've seen the causes of an object being displaced from one position to another by way of a force. You change the object's velocity by applying a net force on the object to go from zero velocity to some non-zero velocity. So now we're going to put the two things together, marry them in this concept of work. We're taking the concepts from chapter 2, 3, back in the day there in chapter 5, marry them together, and this we get the concept of work, which is a form of energy, which we will see as we go further. So work and energy are basically the same thing, conceptually. All right, so the concept of work in physics is defined as a net force multiplied by a displacement, or quantitatively shown, because we don't write essays in physics, to solve problems. So net work is equal to net force times the displacement. It is coupled with each other. The net force and the displacement are coupled, multiplied together, married together, and they move to produce this network. And this is a special case of multiplication. This is a type of multiplication that we call a dot product, meaning that the force and the displacement must be in the same axis. Whether they're both in the x-axis or both in the y-axis, they're going to produce work. So I'll explain further on that. So let's say that we had a box on a surface. We've seen this before. And let's say it moves to the right, and it moves to the right for displacement delta x. Okay, so we got the box moving. Before forces came along, we could figure out how much the box was displaced by knowing a few things: the velocity, the time, the acceleration. So we've seen that so what causes box to move to the right? All right, everybody. Cams on. So right, so we were saying earlier that we've seen the situation where we had a box going to the right under displacement delta x. We can calculate the displacement when we know a few things about what's going on with the box. If we know the, say, initial velocity, acceleration, final velocity, and also if we know the time, we could calculate the delta x. And as we were just saying here, what causes the box to move to the right? Generally, a net force causes an object to go from rest to a non-zero speed. So we've gone from initial velocity of 0 to a final velocity by way of a force. And so that's our picture here. Again, the same box to the right, or even left, under a net force. All right. So when we merge the two pictures, we get this guy. We got the box under a displacement being caused by a net force to the right. So we have a delta X and a net force together. Let's say that this will be our net force arrow, and this is our delta X. As you can see, they're coupled or multiplied together. This is a visual depiction of something being multiplied, working as one unit to move the box to the right. Under the power of a net force, the box is being moved under a displacement delta X. To the right, to the left, up, down, whatever, right? So this picture here, the last picture, we have now coupled or multiplied the net force and the displacement. They're moving together in unity. They're not delta X and then attach a force to it. No, that's simultaneous. That's what's meant by coupling. Again, that's just the English visual there. We have now coupled or multiplied the net force and the displacement. And as we stipulated at the top, the product or multiplication of net force and displacement is called work. That's our physics definition of work. Or as mentioned before, net work is equal to net force times the displacement. Now, as I'm about to write next, you can only have a force can only do work if that force is in the same axis as the displacement, whether it be delta X or delta Y. Cannot be perpendicular. We're going to see why in a moment, but it must be in the same axis, whether it's X, Y, Z, whatever axis. Okay, let's talk about units first here. We know that the units of force is a Newton and a unit of displacement is a meter. So a Newton times a meter is a unit of work, net work. And that's been classified to not just, be called Newton meters, but it's called a joule. A Newton times a meter in the same axis gives you a joule, which is a unit of energy, which we'll be getting used to as we talk about kinetic energy, potential energy, all forms of energy. Okay, so 1 joule or J for short. Now, when we get to torque, we're going to see the same units of newtons and meters, but they're going to be crossed. It's going to be a cross product, and that would just be a Newton meter. All right, we won't call it anything special, but as long as the newtons and the meters are on the same axis, indicated by this dot for, well, mathematically speaking, the dot product, we're producing joules of work or joules of energy. Hence, this is the preliminary reason why work and energy are the same, or they're related to each other. Okay, so as I just mentioned earlier, in order for work to be done by any force, a pulling force, a pushing force, a spring force, a gravitational force, any type of force, friction force, that force must be in the same axis as the displacement. It can be going with the displacement or against or anti-parallel, opposite the displacement. Doesn't matter. If it exists in the same axis, you got some work being performed. Okay. So in order for work to be done by any force, the net force and displacement must be in the same axis. That is parallel or anti-parallel to each other. And I'll show pictures, and we'll see again using the XY plane in terms of the angles, and build the picture on itself. Okay. So for example, if we call this force moving the box to the right, like say a pulling force, so there's going to be work being done by that force. So work done by the pulling force pulls to the right. The above picture causes a displacement delta x to the right. So it moves along. It's in the same axis. It's parallel. The angle is going to be 0. We're going to see that. Displacement delta x, and the horizontal axis for now. We can go to the y-axis. It's the same concept. So let's consider the box being moved to the right. We have done enough work or operation with the concept of forces to understand that when in reality, when a box or an object moves to a particular direction, there's also another force that moves opposite that object or the box in question. And we know that that's going to be a friction force. The friction force is always going to be going opposite the displacement of the box. And since it's moving, we're going to be looking at the moving friction or kinetic friction. If I draw the box again, we have a pulling force that's causing the box to go to the right. The displacement is to the right. And also in the picture, we have kinetic friction as well. And we're going to see why the work done by kinetic friction is going to be always negative work. And we're also going to see why the pulling force work is going to be positive. So we already know already that the friction force is always going to be it's always going to be a negative value. Okay. All right. So I mentioned earlier that the pulling force has an angle of 0 degrees. What would be the angle of the friction force?
180 degrees.
Yeah, it'd be 180, exactly the opposite. And so let's examine that even further. So we have two forces in question here. We have pulling force or the friction force, the kinetic friction force. The pulling force is going with the displacement. The friction force is going opposite displacement. We have a normal force and we have force of gravity. But we're going to see why they're not important in the concept of work. All right. So the work done by the pulling force F pull is parallel to the displacement. And the work done by friction. So we have two forces that are going to be doing some work. Why is that? Can someone remind me why it's only these two forces that are going to be doing work? I just wrote it earlier.
Because the normal force and gravitational force isn't parallel with displacement.
Right, it's not in the same axis. So those are the only two forces. These guys here, the pulling force and the friction force, are the only forces that can do any work, whether positive, negative, or whatever. Yeah. So they have to be in the same axis. So the work done by friction in the same situation. It's anti-parallel or opposite the displacement. Right. So yeah, so we have those two things. The forces must be in the same axis, parallel or anti-parallel. Okay. Go a little further here. So does everybody have this here? Any questions? Definitions, initial pictures? Make sure that this is, tracking that we're clicking this, just introducing a new concept. Okay. All right, so let's quantify what we mean by parallel and anti-parallel. Now that's, again, we don't write a bunch of words to solve problems. So is there a way that we can make a mathematical statement for something parallel and anti-parallel? Let's quantify what is meant by having any force and displacement acting parallel or anti-parallel. Okay. So I'm just going to write a stipulation here first, then show you what I mean in a visual via the XY plane. So we already kind of stated this. So when the net force or any force and delta X are parallel, when they're working with each other, the angle between both of these quantities is 0 degrees. And so then for them being anti-parallel, the net force and delta X, the angle theta is 180 degrees. Anti-parallel, opposite, complete opposite. Same axis, whether X or Y. That's why I stated, so consider the XY plane. In terms of the angles, right? Okay, so we have this guy here, and we know if we do the concept of the unit circle, that the positive x-axis here will be 0 degrees, 90, pi over 2. 180, 270, and then back to 360 to complete the circle. So let's start. We're not going to stop at 360. Let's just starting at 0 degrees. And so if we take the picture from before with the box, and we had the net force acting on the box over a displacement. And let's draw, say, a pseudo free body diagram with the objects represented by a dot in the middle. We can see that our force from that picture up above, say represented by this second arrow, and delta x are parallel to each other, and the angle that exists between them is 0 degrees when they're actually parallel. So, but the friction force, the angle between the friction force and displacement is going to be 180 degrees, or basically looks like this here. Delta x, okay. Right? So, and then up top, it's going to be, we got the objects, so delta x and F net. 0 degrees, this is parallel. And then this is 180 degrees, anti-parallel. So there is a particular function in math that allows the work between these two vectors to produce what we call positive work. And then there's a particular function that allows us to produce a negative work. But before I get to just writing that down, what if I had the same box moving to the right, and instead of the force being exactly parallel to the displacement, let's say that the force say I'm pulling this box with a force at some angle. Well, this pulling force would still produce some work on the box, but it's not going to be the pulling force itself here. It's going to be a part of the pulling force that's going to be producing the work. Can anybody tell me the part of this pulling force that could, or that will produce the work on this box?
The part that's in the x direction, or the part that's parallel to the displacement.
Absolutely correct. And what would that be called here? So if we say this is, if the hypotenuse is the F pull, what would this part be called? And this is theta.
F pull cosine theta.
Yeah, perfect. So we have, oops. So we can just say FP cosine theta here. That's going to be the part of the force that's going to produce work on this box, because this is the force that's moving in the same direction or parallel to displacement. The sine component doesn't. So he doesn't matter, or he's not going to be producing any work in the system. So a generalized equation for work would be this. Net work is going to be F net cosine theta times delta x. Now, in the case when the net force is in the same direction as the displacement, the angle is going to be equal to 0. Cosine of 0 is just 1, so it just becomes F times delta x, F net delta x. Oops. So this is our generalized, generalized work equation. The cosine component goes away when theta is equal to 0. One quick second. Okay, I'm back. So let's get another question here. Okay, question is, yeah, exactly. you and Emmanuel answered correctly. The horizontal component of this force is going to be performing work because it's in the same axis as the delta x. So let's say when angle theta is equal to 0, then it just becomes F net cosine of 0 degrees times delta x. This here becomes 1, so it just becomes our equation that we started off with, F net delta x, the easiest case. So with that generalized equation being derived there, we can get the work that's done by the friction force. So we can say, instead of just net, because we know that net is going to be the total amount of work done by all of these different forces, let's just be very specific about it. If we wanted to find the work that's done by the friction force, then we just have F of friction, we know it's kinetic friction, cosine of 180 degrees times delta x. You know that cosine of 180 is what? Cosine of 180?
-1.
It would be -1. So therefore, this is just going to be negative FF delta x. So the work done by friction will always be a negative amount. It's always going to take energy out of a system. We'll be dealing with that when we get to conservation of energy. But okay, so this is a kinetic friction, and we can just simplify this even further. Fk delta x. So we can just say the equation for kinetic friction, which is mu k Fn delta x, to be completely explicit. So work done by friction with this would be this. So when we know your mu k, your normal force, and your displacement, you can get the actual value of the work done by friction. So all of these different forces have their own work component. So the work done by the pulling force, just go here and be very specific there. F pull delta x, work done by friction, FF delta x. And we have a question. So we always do friction separately from F net. That wasn't the point I was trying to make here. I was just saying that you can calculate the work done by any force, knowing the angle between the force and the displacement. So it's not a separation. But to synthesize your point, once we do get the work done by the pulling force or the friction force or any other type of force, we can add them together to get the total work. Because remember, just like force and net force, net work is comprised of the individual works. Work done by friction plus work done by pull, whatever, gives you the net, similar to net force, the force done by friction, and so on. Same concept. All right. So let's do a quick example here. Before we get to that, so I will now show you the box again. And let's say that we do a free body diagram on the box. So we have the normal force like this. And of course, we have the pull force and displacement. Actually, from my previous example. Let's say we had the pulling force like this. And as Emmanuel and Nicole stated, it's the cosine part of this force that does the work because it's along the same axis and it's parallel. So then let's have the, we know that the work done by friction is going to be negative. It's going to be 180 degrees. opposite the displacement, and then force of gravity. So let's get the work that's done by the normal force, if we can. So I just say Wn is normal. The angle between the normal force and the displacement is 90 degrees. I can just put displacement down there because we know it's along the positive x-axis. So normal force, displacement 90 degrees. Cosine of 90 is just 0. That's really why there's no work done by the net force or the normal force, because cosine of 90 is 0, so the whole thing is 0. 0 joules of work done by the normal force. And conversely, by gravity, in this configuration, work done by gravity is going to be Ft cosine of 270. Cosine of 270 is delta x, or is equal to 0 if you put it in your calculator. And that also produces 0 joules of work. By our generalized definition of work, it's the cosine component that does the work. The cosine component is along the axis in question, in this case, along the x-axis. And then when we have falling objects, it'll be along the y-axis. So, thing to keep in mind, no matter what orientation, is your force in the same direction as your displacement, or is there a part of that force that's in the same axis as displacement? Okay. Okay, let's get to an example here. Okay, let's go to question number 1 of your textbook there, page 189. As you're turning, I just want to generalize the work equation even further. So we've already stated that the total amount of work done in a system is equal to net force times cosine theta delta x. Now, let's pretend that we were looking at an object moving in 3 dimensions. We would be looking at all of the work done in the x plane, the y plane, and the z plane. So therefore, we could further generalize this equation and say that the total work done in the system is going to be net force cosine theta times delta r, where r consists of the x, y, and z plane. Here we're doing just the x-axis by itself. We could do the y-axis, it's going to be f net cosine theta delta y, z-axis f net cosine theta delta z. But this would be a situation when we're considering all 3 at once. We just had a z plane, x plane, y plane, and it's kind of hard to draw the radial vector. Let's see. Something like that. We'd have the z component coming down like so. Yeah, kind of tough to visualize, but this would be the r vector, or the radial displacement, which would be the sum of all the x and the y and the z components together. But, so this here, this would be x. Let's say this would be z. This would be y, and this here would be y-axis again. It's just the transformation of y here. And this would be this guy here would be my z-axis. So the r just represents all 3 at once. But again, most of the time we'll just be looking at the work done on each axis one at a time, x, y, or z. All right, so page 189. Number 1. So why don't you guys try that out? Slides right now. You can work on that for a few minutes. You can stay right there if you want, but no need to break out. So we have a block of mass, 2.5 kilograms, right? Pushed along 0.2 meters along a frictionless horizontal table by a constant 16 Newton force. Directed 25 degrees below the horizontal. It's important that we get that picture accurate. So we have a box that looks like this, below the horizontal like that. And it's moving along. So this is the component that's going to be, along with it's going to be moving with the displacement here. We have the displacement. It's going to be the cosine component of this force. P cosine theta. F sine doesn't matter now, not unless it was falling. And got a mass. Okay, so now we want to determine the work done by the applied force. So we're doing one at a time. The applied force here, the FP in this case, the normal force. We want to see how much work is done by the normal force and the gravitational force. And then determine the net work, which is the sum. Take a few minutes to do that. Any questions? I don't know how to set this up. Just fire away. The general equation for work: net force cosine theta times displacement. Now we break that into bits. You want the work done by the applied force, which would be F applied cosine theta delta x, and then normal force, and it's N for short, I guess, Fn cosine theta delta x. So we're always going to be locating where the force in question is with the displacement. What's the relationship? So like normal force was perpendicular to delta x, so there's no work. Cosine of 90 is 0. And so on. Okay. And so forth, and then the net work would just be the sum of the work by the applied force, normal, gravity, that will do it. Let me know if you have any questions in a private message. All right. Let's calculate each of these parts. So yeah, part A, we get the work done by the applied force. Well, it's the force applied, cosine theta delta x. Let's see what part of the force. So this is at an angle, so we're going to take the cosine part, multiply by delta x, so we have our work done by the applied force. Too bad. 16 newtons, cosine of 25. Sure, my cool terminal, blah, blah, blahs. Okay, and 2.2. So what do we get for that? hopefully what we got is correct answer there. So 28.9. All right, let's see. Verify. I'm gonna trust you. Huh? 2.2. Okay. Should be 31.9. Did anybody get that? Yes, yes. 31.9. So I would check that again. Who got the 28? Yes, 31.9. Not newtons, but joules. We use the joule, newtons. Awesome, guys. We want to get the concept of, we want to have the force and the displacement the same direction. Whatever the axis is, it could be opposite, it could be with it. Just be in the same axis, parallel or anti-parallel, and you're good to go. And since they work together, it's going to be positive work. Good. So, right, because they're moving parallel to each other, the cosine part. So real quick, Selena, how much work is done by the normal force? I mean, or is that a quick process?
Can you repeat your question, Mr. Kelly?
I'm sorry.
Did you ask a question?
Yes, I was asking you, what did you get? What's the work done by the normal force?
Oh,
Okay, let me paint the picture here. There's displacement right here. You see this?
Yeah.
Normal force would be here. Ah, boy. What's the angle between the normal force and the displacement? Okay, I'll just do it right here instead. What is this angle?
90 degrees.
Okay, what's the cosine of 90?
Like, what's the sign for it?
No, the operation. So put in calculator and say cosine of 90. What does that equal?
Oh, okay, let me do it.
Okay. I don't like this. Leave it alone. Yeah. Cosine 90. Equals, should be 0, right?
Yeah, I got 0.
Okay, cosine of 90 is 0, therefore the work done by the normal force is 0, because when you put normal force, it's weight, normal force is going to be mass times gravity, cosine theta times delta x, and whatever this is. Okay, who cares? Because cosine of 90, that's the thing. When this is 0, the whole thing's 0. So this is why the work done by the normal force is 0 joules. No action done by the normal force, no work. Okay, and then frictionless. So what's the work done by the gravitational force, anybody?
Zero.
That will also be 0, because the work done by gravitational force, 270 degrees, if you know the orientation, depends on your perspective, unit circle, or you're going to go from the, clockwise, it's still 0, either direction. So gravity, also 0 joules. So no friction, so we don't have to worry about that. So that's a bit on that. Let's see. Let's do question 2, and that'll be it for this section. All right. So we got a raindrop, very small mass, of course, 0.35 times 10 minus 5 kilograms. Falls at a constant, falls vertically at constant speed. So when you see the constant speed, what do you know about the forces acting on the object? Anybody? When something moves at a constant speed, what can you say about the net force on that object?
It's 0.
Yeah, it's going to be
equilibrium.
equal to 0. Right. So whatever forces are involved will be what?
Equilibrium.
There's going to be a state of equilibrium. So let's say, okay, so we have the raindrop here. And let's say that it's, air is pushing up on it. And of course, the force due to gravity is going down. So when you add those two forces together, yes, the total amount is going to be equal to 0. The net force, Newton's first law of equilibrium, has a case where the net force is equal to 0. Now, that being said, we can say that the forces that make up the net force are going to be equal but opposite. So this is negative going down, and this is positive going up, the air resistance force. Now, keeping that in mind there, as it falls 100 meters, what is the work done on the raindrop by the gravitational force and the air resistance? Could you say that the work done by both forces is equal or not equal?
They're not equal.
Why not?
Um,
We know that the forces are equal.
Because it's falling.
Okay, the object is falling, but don't lose focus on the forces. They're equal and they're opposite. Yes, it's falling. If it's falling, surely not. The gravitational force must overcome it. Okay, so here's the deal. All right. It's moving at constant speed. These forces are equal. Okay, these two forces are equal but opposite. So one's pointing down and one's going up. And we know that work is equal to any force times the displacement. Since these forces are equal but opposite, the work done by both those forces is also equal but opposite.
So 0, is it 0?
The total work will be 0, but individually they're going to have a value that's going to add up to 0 because it all goes back to this direct relationship here. So the work done by the air resistance is going to be the force of the air, cosine of 0, well, let's see, cosine of theta, delta x. We look at this raindrop. The raindrop is falling down. In this case, it's delta y, not delta x. The work done by the air resistance will be opposite the displacement. So the angle is what? So the displacement is down. The force of the air is going up. What's the angle between them?
Is it is it like 90 and 270 then? Or is it
Is it 180?
Yeah, it'll be 180 because now,
Oh,
yeah, we're changing our perspective from the x-axis to the y-axis. So with respect to the x-axis, yeah, that's going to be an issue, but now everything's along y. So everything that moves with the y or going down, the force that's going down is the force of gravity. So the work done by the force of gravity will be positive, but the work done by the air resistance will be negative because it's going opposite. You see that? Okay, so the question is, if a force isn't overcome by another, how is vertical motion occurring? Because the forces are equal. So we have a situation where we could either be at rest or at constant velocity. Remember Newton's first law. Newton's first law states that if an object's at rest, it's going to stay that way if the forces are equal. If it's in motion, as this raindrop clearly is, and it's moving at a constant speed, the forces are equal. Neither of these forces is bigger than the other one. They're the same. Yeah. So, no, you're not. Okay, let's just calculate it. And I gotta buzz out. Don't worry, that's why we're gonna, just do, and we're gonna have many examples here. Okay, so the air, so this would be cosine of 180. We all see that, right? Do we see that air is pointing up? As the raindrop falls down, displacement is down, but the air resistance force is up as the displacement is down. So the angle between the air force and the displacement is 180. They're opposite. But the force of gravity and the displacement will be 0 degrees because they're moving parallel. All I did, or all this problem is all about, is taking the box problem and flipping it on the y-axis. So anyway, that's going to be multiplied by 100. You guys can calculate that. Work done by gravity will be force of gravity and its displacement, mg delta y. They're moving with each other, so the angle is 0 degrees. And cosine of 0 is just 1. So the work done by the force of gravity and its displacement will be positive, 3.25 times 9.8 times 100. And so this will be -1. So the work done by the air resistance will be negative. The work done by gravity will be positive. We're going to come back to this and others and more and get this locked in. Okay, for right now, I got to take off. You guys take it easy. See you. Oh, hopefully I can see you at the office hour session. Okay, because I want to do more examples.